My name is Evan Fick, and I'm from South Dakota State University. I'll be presenting on the Talaria Running Form Trainer device for the ASME Old Guard Oral Presentation Competition. This presentation is going to highlight a device that is used to provide instant feedback to improve outcomes for endurance runners, as well as store information for in-depth statistical analysis on their runs. The inspiration for this project is a book I read by Christopher McDougall called Born to Run. The book highlights a tribe of native Mexicans called the Tarahumara. The Tarahumara run an average of 20 miles a day for the adults, from village to village as a form of socialization and just a way of life. And the book contrasts the Tarahumara's low injury rates with their thin sandals and high mileage to the injury rates of American runners who have better access to medical care, better nutrition, and more highly cushioned running shoes. The book goes on to posit the theory that these highly cushioned running shoes, rather than helping prevent injuries, actually cause them by allowing runners to run with worse form by covering up the feedback that your body would normally give you if you were wearing less cushioned shoes. For example, hitting the ground with your heel first in a heel strike running form is a painful thing to do barefoot, but with cushioned running shoes you can get away with it. It's still not good for you though in the long run, as it puts more forces on your knees and your bones. The foot is sort of functions as a spring, where the arch of the foot is meant to absorb the impact forces of your foot hitting the ground in every stride when you're running. And so when you run with heavily cushioned running shoes, you can move away from the more forefoot landing that allows you to use your foot as the spring that it's designed for, and towards a heel strike, which leads to more stress-related injuries. So myself and many of my teammates, actually 6 of the 12 endurance athletes on our cross-country track team in my grade, have experienced a stress fracture over the course of their career. Stress fracture is a break in the bone that occurs not due to like a sudden trauma, but to gradual repeated pounding on the bone and high forces on the bone that causes a break. The recovery for these injuries can range anywhere from 4 weeks to 12 weeks, and even after that there can be complications. And the especially tricky thing about them is they typically occur during the higher mileage portions of our training, which happen in the first half of the season. So a lot of athletes who will end up with a stress fracture will lose their entire season to the injury. It's a really heartbreaking injury. And so we wanted to come up with some way to apply our engineering skills to reduce the occurrence of these injuries. Before we did that, we wanted to do some background research and ensure that the literature reinforced our idea here that we could reduce impact forces and reduce the incidence of stress-related injuries. And we found that, in fact, it does. People who run with a heel strike have approximately twice the rate of repetitive stress injuries than individuals who have a forefoot strike. Now, here's an illustration to kind of give you a better sense of what I mean by the word heel strike. When you strike the ground with your heel first and toe up in an exaggerated heel strike form like this, the forces, rather than being absorbed by the arch of your foot, are going to travel directly up your leg, shock the bones and the knee, and lead to higher injury rates. Whereas if you land with more of a midfoot or forefoot strike when the foot initially contacts the ground, you can absorb those forces. These diagrams also well illustrate what I'm talking about. This is a heel strike where the runner's foot is out in front of their body versus the midfoot forefoot strike where their foot is comfortably underneath their body. Another incidence or another cause of heel striking can be trying to stride out or take larger steps than what's natural for you. And so another thing that you can do to try and reduce incidence of heel striking is take shorter, quicker steps. This graph over here shows the curve of the impact forces the darker one being heel strike impact force, and the lighter gray one being forefoot impact force. So you can see that the rear foot strike has a much sharper slope of the loading rate, and that sharper sloped loading rate leads to higher injuries rates. So we wanted to create some kind of an electronic device that would collect force data from 5 different locations on the foot that could provide real-time correction for the athlete through a buzzer, could facilitate post-run analysis by collecting all this information and storing it, that wouldn't impact the performance of the shoe itself, and had the capability to store up to a 2-hour run. We also wanted to conduct an experiment with a number of people and prove that our device was in fact effective in training people's form. And we wanted to build a business plan and a plan for manufacturing these on a large scale moving forward. So the first step in the development of our business plan was seeing what other devices there might be like this on the market. We found Aerion, a Dutch company that sells their device, which is pretty similar to what we hope to build. They sell their device for $300 each and target almost exclusively professional athletes who are trying to make small tweaks in their form. They don't sell in the United States, and they don't sell many units in general. So another similar product is produced by TechScan and used by biomechanists to analyze their patient's form in a lab on a treadmill, but it's hooked up to a computer. It's not a mobile standalone unit like we hope to build. So here's a little demonstration of where we are collecting the force data from. We use 5 force-sensitive resistors in a thin sheet that can slide underneath the sole of the shoe and uses a voltage divider and analog inputs to read the resistance of those sensors and thus the force data. We wanted to use an Arduino microcontroller to read this information, to perform the data analysis, to store the information, and to send the signal to a buzzer to provide the feedback. Here's another table that shows some of our objectives for the device and an early form factor idea that we had. In selecting our microcontroller, we wanted to go with an Arduino one because that's what the members of our group had experience in programming and using. And we considered a number of different options, but ended up selecting the Nano, which gives us easy interface with the computer for uploading code and monitoring those analog inputs while we're still in the testing stage, and also a very small form factor that wouldn't be obtrusive attached to the tongue of a shoe. We also learned that the Nano's power consumption is very low, and we could get away with using a 350 milliamp hour battery, which is very small, and it would give us about 20 hours of runtime. Here's a little overview of the force-sensitive resistors that we used, some of the testing that we did with the force-sensitive resistors to prove that they could withstand up to 600 pounds and still give reasonable data, and the voltage divider that we use in our device. So we wanted the microcontroller to be able to read the voltage input and read it at a reasonable sampling rate to get the information that we needed from the device, to write that sampled data to a micro SD card for later statistical analysis, and we wanted real-time analysis for it to write that signal to the buzzer to indicate when the athlete's form is breaking down. So our first prototype we built onto a breadboard with through-hole components. Here's a circuit diagram displaying all the different parts of it and a picture of the prototype itself. Now we had quite a few problems with this one. The soldering turned out to be kind of ineffective. The device was unable to power on. It was very compact, and we were glad to see that we could get all the components we needed into a board this small, but the board was disorganized. We didn't plan it out very well beforehand. We just kind of built it as we went. The sensors also on the pad were too close together to collect the information we needed. So we pretty quickly started working on our second prototype. Now for our second prototype, we wanted to use an RC filter to filter out some of the noise that we were getting on the analog inputs. We used a 0.1 microfarad capacitor in parallel with the resistor in our voltage divider to help filter those a little bit. We also went with a single inline pin resistor for the 5 resistors used for the voltage divider. It shares a common ground with 5 different resistors in a single small package. So it helped us stay organized and much more compact. So as you can see, this circuit diagram for the second prototype is a lot more complex. There's a lot more components to it, but we were able to keep the actual package smaller than the first prototype and very well organized. Here's 6 of the different units that we produced. We ended up producing 10 of this prototype, and these were also the units that we gave to the people in the study. We tried some different materials for the pad that held the force sensors in it, just to see what would be effective and what wouldn't. And here's another picture of the device with the Arduino microcontroller soldered in place. Our third prototype is currently under development. We want to move to a PCB with all of our components on it. That way we can keep those parts of the Arduino Nano that we use and appreciate and get rid of the ones that we don't need to cut weight and size and expense moving forward. We can also have things like the microSD driver built into the PCB board. A single PCB board also gives us greater hardiness, and in theory it's going to be cheaper moving forward to scale up in manufacturing, and it's going to be much lighter than our current prototype. So I mentioned a little bit about our study. We have a 10 participant study right now who ran with the device. Now, because of the pandemic and some hardiness issues with the prototypes, it's kind of come to an end now. But we got a couple weeks of good data from our different participants. We fixed them as we went, and we at least have a lot of statistics to analyze in our statistical analysis software and start to find some of the trends that we're looking for in the athletes. And we were able to see that some of the athletes had form that would indicate the buzzers, some of them wouldn't, and some athletes, while running with the buzzer, were able to alter their form to get it to quit buzzing at them, which is exactly what we were hoping for. Here's an overview of our budget. I really want to highlight that our cost per unit was all the way down to $28, especially considering that these are short run units and we're still ordering parts off of Amazon.com, for example. We're really pleased to have a price point that low, especially considering the only similar product in the world sells for $300 per unit. So I want to say thank you to my fellow team members on the Talaria Running Form Trainer, to Anna Fozen, to Caleb Bray, and to our faculty advisors, Dr. Stephen Gent, Dr. Tim Hansen, Dr. Brad Bowser, and Coach Ann Bears. All of their guidance has been absolutely crucial to helping us get this device from an idea to a third prototype in progress. And I also want to say thank you to Dr. Mikna for encouraging me to participate in this competition. Thank you.